today. We have Sanjeev Arora, who needs no introductions. So Sanjeev is at Princeton, and we all know him from his book on computational complexity. In the last few years, Sanjeev has been working on several interesting problems that are related to language models and their skills. And so he'll be talking about some of those problems.
Thank you. Yeah, so this is about LLM skills and metacognition. So I'll start with the obligatory joke. So actually, I gave a talk at Simon Institute about a year and a half ago, like 2023 summer. And Alyosha was giving me a hard time because I was talking about skills even back then. And he was saying, oh, they're just like parroting back things. So anyway, so this was, they obviously cannot understand since they only do next word prediction. So I asked GPT-4o, and I said, generate other examples of this, and it does this. Okay. Everybody's been talking about how there has to be something better than next word prediction, and still seems to be going strong. So motivation for today's talk. This is a high-level motivation. I won't really do much of this. What are high-level ways to think about LLM training, or in other words, communicating to LLM what you're trying to make it do, besides just gradient descent on next word prediction loss and its variance. And of course, and in the previous talk, it was actually almost very explicit that, we shouldn't think of SFT and RL as too different. RL uses the same loss, but, sometimes there's gradient ascent, right? Because negative reward versus positive reward, you use the gradient in opposite ways. Okay, so that's the high-level motivation, and I think one way to possibly get to that is by thinking about skills more explicitly. And facts is the way when people say, okay, what does the LLM know? People talk about facts, but we should think about that in terms of skills. And nobody has ever given me a very clean definition of what a skill is, except sort of tautological. It's a way to do something, procedure. But we all know a skill when we see it. Although I'll get to some surprising examples. And yes, being procedures, they can be chained together. So let me argue that next word prediction requires learning procedures, and maybe for this audience, this is maybe obvious, but let's just think about it. Suppose the term metaphor didn't exist in English. I claim that you'd still have an intuitive concept of metaphors and how to create new ones. And in fact, a 10-year-old might already have this, even if they've never heard the term metaphor. They might have encountered phrases like this, right? And so even a 10-year-old would realize that sometimes adults talk in this way when it's not literally true, but it's like you can see the analogy, and then similes and other variants. And so it's easy to see that any entity that learns to do next word prediction, if it has to get good enough, will be able to predict, will need to be able to predict this, and therefore would know about metaphors, right? So it would have some idea of how to create new metaphors, right? Because often metaphors you haven't seen before, but you understand them. But why metaphors? Basically, all complicated reasoning is procedural. And here's an example, okay? Continue with metaphor. Give me an example of a piece of text with 2 sentences, which could appear in a fiction about sushi, and has these 2 skills. Now that's a kind of strange prompt, which you imagine, would not naturally occur. But yeah, GPT-4o has some reasonable. This was in 2023, so it's a year and a half ago. Could already produce these things. These days, the models are even better. Okay, so you can see that yes, there are procedures, but it's not like programming language, right? It's not clear what this composition is and how it's achieved. There are no rules for it, no formal rules. And then the question is the model just copying from training data? And that was indeed the reason for doing this kind of evaluation. This is from a paper of ours, the skill mix evaluation. And what we found was that GPT-4o could do these kinds of synthetic constructions for up to 5 skills at a time. And these skills were randomly chosen from some long list. And also the topics were not too common. And a probability calculation suggested that most of those successful generations were novel, unlikely to have been seen in training data. Just because training data, using some estimate of the size of the training data. And it was verifying this theory that we had. And I'll say more about that later. OK, so that was about skills, just warm up. And which leads to the topic of LLM metacognition. And again, it's motivated by this question, which Alyosha was very interested in a year and a half ago. Like, are they really aware? Like, are they just parroting things? And this term metacognition, or this LLM metacognition, is from this paper. OK, so before asking, are LLMs aware of what they're thinking? Well, of course, LLMs are not aware in the same sense. The moment you power it off, a new session starts. But how do we know that humans are aware of what they're doing? So when you see a math question like this and you start solving it, humans can have this, call it chain of thought or whatever, some exposition of what they're doing, how they're doing it. And that's called metacognition, the reasoning about their own thought processes. And these terms are well known in pedagogy, and they're used to improve human learning. For example, if a child has difficulty reading, there is a metacognition theory for how to improve reading. OK, so you can elicit metacognition in LLMs. And this was the original method that we used in that paper. And this is the simplest one. So here you use a task. So let's say math or GSM-8Q, or any of these usual data sets, problem-solving data sets. And you give these task examples to a powerful LLM, subject to context limit. And you ask it to label it with skills needed for each example. And you give it a format for the skills, labels, like they are strings of 4 words connected with an underscore. So it's very expressive. And then you can feed that list of all skill labels to the LLM and ask it to meaningfully, to semantically cluster them. So, I mean, this is being used more and more. I mean, this was more than a year ago. But yeah, these days, these methods have become very common. The novelty here was to ask it to label skills. And then these clusters were also labeled with skills. OK, and at the time, there were some other papers that were trying to identify traces of human skills in LLM activations, but that's very different. OK, the LLM generates these skill names. So these were the kinds of skills that were extracted from the math data set, the Hendrix math that was created at Berkeley. So you can see, each skill consists of up to 4 words, but you can sort of understand by looking at those words what those skills might be. OK, so in that paper we had these uses of skill catalog. So you could improve K-shot performance by providing skill-relevant in-context examples. So that was in that paper already. So K-shot problem solving was greatly improved if you actually provide skill-relevant in-context examples. And then in the Llama 3 paper, it was also used for data selection during instruction tuning. They mentioned this method. So you see this, and you look at those lists, and they look kind of like what you might see in some math pedagogy book or Khan Academy or something, right? These are your skills. So that's the natural question that arises. And well, in that context, that could be a reasonable conjecture that it's just parroting something it's seen in some math pedagogy book. But I'll argue, and you'll see some more examples, that the phrasing, I think, is repurposed from human pedagogy, this idea of skills, etc. But the skills were derived from internal analysis of the training data. That's my guess. And let me show you method 2. And this one is you just ask the frontier LLM to give examples of skills. So here's a sort of way to elicit interesting things, and you can go and try this. A broad skill that has no existing name, but which many humans will recognize. So GPT-4o said linguistic exorcism. So I immediately went over to Google and typed it in and didn't find anything on Google. So I said, okay, what are some sub-skills? So it gave me finer grained skills associated with that. Got this. And then even give finer grained skills under the first one. And it gave me these. Synonym substitution technique. He's lazy and useless. He prefers a relaxed approach and is still finding his strengths. And tone moderation adjustment, that one. Let's focus on how we can improve this. And so then you realize what's happened. So this is similar to the metaphor example, right? As it did its pre-training and post-training, it recognized that humans have this skill or tendency to be able to reword things in a different way. Make it less offensive, more useful, etc. Encouraging. And it came up with this concept existed in there, right? Because it needs it for next word prediction. Right? And I'm not suggesting that it had come up with this hierarchy. These things were all continuous inside, right, in the parameter space. And then when I asked it this question, it sort of condensed that continuous information into this discrete way. Another example, okay? So now this is Gemini 2.5, which I'm actually very impressed by. So it gave me intuitive object placement. Gemini, okay, let's see, okay. Give me fine-grained skills associated, same question. Edge-aware placement. What is this? I asked it, what is this? So it says, when you put down something on a surface, you make sure it's not on the edge. It will fall off. You're edge-aware. Stability assessment, like it can roll off, whatever, right? You sort of evaluate that before you put it down. Implicit item clustering. When you're putting down a lot of things, you intuitively cluster them by category. What the heck? Now, I think here it might be relevant that Gemini 2.5 Pro is a multimodal model. It's the latest one. And so maybe that's where it's getting this, because this seems very embodied skills. Yeah. Any reactions?
Don't we all do this? Don't we all cluster items?
Totally. Yes. Except we'd never even thought of it as a skill, never given it a name. This is metacognition. Okay? In training on all this stuff, they have really developed very sophisticated understanding of things and taxonomies and hierarchies.
You did search the web if somebody has written a book about this thing, right?
Yeah, I mean, I didn't get these. At least the terms are not there, so I don't know how to search the web otherwise, yeah. But you can do this with all kinds of things. That's my point. It's highly unlikely that all those books exist.
Well, why does next word loss induce metacognition, though?
Good.
Cognition.
Good. Okay. Oh, cognition.
Well,
cognition. Yeah.
Why does it induce in it the ability to identify, name, and tokenize into English these concepts?
Yeah. No. So it's an open question. Let me have speculation. So yeah, I mean, I'm a theorist, as maybe some of you know. So I do like to think, I would want to have a theory for it, and I'm working on it. But this is speculation. That an LLM is also a theory builder for text pieces. So suppose there's a text piece like this, and this is actually a joke because many of you may know from the old NLP days that the city council thing was a classic Vinograd example of a piece of text with multiple meanings. Okay, so this was actually generated also by Gemini 2.5 Pro, and it alluded to this history of why it's an interesting one. So anyway, you put it into LLM, And now you realize to generate the next word, the LLM has to analyze this and has to have some kind of theory for what this piece is doing, right? What is being discussed. And this next word, is it related to the budget focus or the environment focus or the consensus focus, right? All of those are being referred to, right? There's environment, there's like sharply divided people, there's a budget issue. Those are all the moving parts in this. And the next word prediction could depend on some or all of them, right? And so it may have some probability on all these words which correspond to the different foci. Okay. Yeah, so this is my best guess of what's going on. And so as the LLM is doing the next word prediction, it's building this theory, or call it a mini theory, for that piece of text. And of course, they're all using the same circuits. Okay. And so it was very interesting. Just last week, this paper came out from Anthropic, where Anthropic is very interested in mechanistic understanding of thinking inside and finding circuits. So at least for small pieces of thought, not this long, like 10 words or something, they did find circuits that are like classifying the context into classes, exactly kind of like this. So I was very intrigued to see that. This is speculation, an aside, and the hat appears to Anil. Is Anil here? Oh yeah, there he is. So he learned about metacognition, and he said, oh, this reminds me of this theory for consciousness. And actually, he arranged a very nice panel discussion at Princeton a few weeks ago. So, there are many theories for how attention arises, and this theory says, look, we clearly need to have a circuit that has some self-image, right? Like if this lady is wearing a hat and gets into a car, has to have some self-image, right? So that the hat doesn't fall off. And actually, that comes from some in the paper they mentioned. There was some woman who had a lesion or injury to the head, and she couldn't do this anymore. And that's when they realized this is a skill that lives somewhere in the brain. And so the theory for consciousness is just we have this self-image, and then that same circuit can be repurposed to think, okay, I'm not just looking at it, I'm looking at an apple, and that's me, I'm looking at an apple, right? So it has this self-image. Okay, so these circuits can be repurposed, and I think that's what's going on. But I don't have more rigorous way to say this. Okay, so what good is metacognition? So you can generate synthetic data. Now, people have been generating synthetic data since for many years. So this was a project we did in 2023 as well. So synthetic trained data for instruction following. Now, there were these open efforts like Alpaca and Dolly, etc., to teach a model, a base model, instruction following. And those didn't work very well, compared to the proprietary models. And so our method was very simple. So using LLM metacognition to get GPT-4 to produce a long list of instruction following skills. So just say, hey, you are a great chat agent. Give us these skills in this format. And it gave us those, hierarchy, etc., about 1,000 skills. Using this list, randomly pick pairs of skills and ask it to produce a plausible user query and answer, exhibiting that. Okay, and now using this data set of merely 4,000 question and answers. In industry, people use tens of thousands, if not hundreds of thousands. Alpaca had 50,000. UltraChat had 1 million, right? This is 4,000 question and answers. Llama 3 8B base model got to a level on Alpaca eval, okay, which is just an open eval, better than Opus and 405B. And so that was a kind of interesting finding. So this paper has all kinds of other findings about what can hobble instruction tuning and so on. So just the instruction tuning process can be studied with this synthetic data set. But anyway, that's the headline number. Yeah, so this was way, way better than anything anybody had ever achieved, starting from a base model. And it's just SFT. So it ties into, Alex's thesis that SFT from a powerful teacher can be very strong. Okay. All right, so why was this so good? So here's an example. So these were two of these skills, critical thinking and communication, literature and language skills. And this was in the context of, I think, teaching. And it created this question. It's a very long and detailed question with many moving parts. And it really forces the base model to learn to retrieve all this interesting information from its internal parameters and put it in the answer. And contrast with existing open data sets, like, very simple questions, or at least not as many moving parts. Okay, we also did this for math data sets. So we again created questions using random pairs of math skills. So we extracted those math skills that you saw before, and we created these random pairs and then use agentic use of frontier LLMs to create reliable answers. These questions were actually fairly interesting, because unlike in the math data set, they were going across topics and combining like algebra and probability or something, which didn't occur in the original data set. And we've got these results, and all models dropped in performance. And at some point, we realized that there was a very simple explanation for the drop, which is you rescale. So if x is the original performance on math, and on math square, your performance is y is equal to x squared. It's a very good fit. And you can see why that happens, because it's using random pairs of skills. So if you have some probability of not applying the skill correctly, you would fail. Okay, so that's why you have the square. Okay, any questions so far? Yeah. Sorry. Oh, for math, yeah, this is exact match. Okay. Yeah, so all of these questions also had exact meaning verifiable. Yeah, whatever. Yeah.
So what are the examples of math skills here?
Oh, there was a slide earlier. I can go back. These kinds of skills.
Give me a question that requires understanding circle properties and
probability.
And I see.
Yeah. So they were interesting questions. Yeah.
Yeah.
More interesting than these. Yeah. Yeah.
So when you think about these skills, right? Normally, from an economics perspective, you would look at something like a production function, and you would look at an output from the production function, right? Then the skills can be complements or substitutes, and be very interested in understanding that. But many times, just understanding what the skills are can be very hard given a data set, right? Yeah. Some easy data sets you might be able to tell, okay, these are the skills that are there that I need to have.
Yes.
But sometimes, just that skill identification can be a super hard task, right?
Totally agree.
And if you don't get that right, I believe, I would assume that, things don't go so well, right? Yeah. I don't know if you've tried it with some harder data sets and have some results to report.
Yeah, so I think that's a very good question. So what is a skill, ultimately, right? And it's not well defined. And in that math example, right, it's not like when it says, okay, probability skills or whatever, trigonometry skills. I mean, you can have arbitrarily hard difficulty, right? And I think that skill is, in that context, just the skill needed to solve questions in that data set, right? It's not, okay, yeah, skills, that same skill or the same name for graduate level problem solving. Yeah. So name it can be used in both contexts, yes.
Also overlap between the skills.
Yeah, all of that.
That's
so I already said, right, so this, when we ask it to list it in this discrete way, it's condensing this continuous blob of things it knows into these discrete categories. So yeah. Yeah.
Do you find that the names of the skills and the sub-skills came from a teacher and the same teacher?
I don't think so. Like my Gemini 2.5 Pro example, I would be very sure.
So it's not that it matters that I can take the same names of skills and ask DeepSeek R1 to produce questions.
That also would reasonably work, yeah. I mean, not exactly, right? They might have slight differences in what they think of those skills.
It's not that the same person has to name the skills and then use them.
No,
Okay.
we've tried this. Yeah, I forgot to mention that in our paper on metacognition. We showed that they make sense to other models also. Other frontier models, yeah. So yeah, this is exactly where we are anyway, which was my next point. What is a skill? There's no rigorous definition. How do we reason about any of this? Okay, so we're talking about semantics here, right? Semantics of language. And okay, in the context of skills, but in general, semantics, there's no agreed upon framework which captures everything. Okay, these are just some buzzwords that people have used in language semantics. And then even harder is to reconcile this framework of categorical grammars or something with the simple statistical viewpoints that we use in LLM training, right? Like cross entropy. So I'll just give you a quick overview, like 1 or 2 slide overview of, maybe it's even 1 slide, of this theory that we did, Anirudh Goyal and I, back at DeepMind when I was visiting. So here's a quick overview. So it makes some assumptions. So there's a set of S of underlying skills. So we don't define what are skills. There is a set. And skills can be composed. And our complex skill is, composition of R skills. The second assumption is that pre-training data is a stream of finite text pieces. Okay, you can think of it as the length of a context of the model or something. So it's a finite text piece, and comprehension of each text piece relies upon K skills. Okay, so this is all just assumed there is some set of K skills that are relevant to this text piece. And the third assumption is that the text pieces are drawn from an unknown distribution via an unknown process, but the latent distribution of the skills is a product distribution. Okay, so this third one, it takes a while to even understand what I'm saying. So impressionistically, maybe this makes sense. Okay, so the main theorem that was proved by, not provided by, random graph theory is that the scaling laws at the time, for example, the chinchilla scaling laws, which describe, as you scale up the model, how cross entropy goes down, scaling up the model by 10x allows it to comprehend text pieces with twice as many skills.
So is that the log? What's or square root? How did the 10x and 2x come?
Yeah, so just from the chinchilla exponents and so on. It's a very rough thing. 2 is approximate. It wasn't there. It's not an integer. It's about that.
So you take as an input to this theory the fact that the loss
goes down
as a power law in model size and data set size. That's the input to
right, and they recommended that the data scales proportionally to the model size. Yeah.
And how does graph theory use the scaling law?
Yeah, so I'm not doing the proof, but if we have time, I can say more. Yeah.
But it's
yeah.
theory.
Yeah. So it uses. So the random graph theory comes from here. That the latent distribution of skills is a product distribution. That's all you need. That's where the random graph theory comes in. And then the rest of it is like advanced playing around with random graph theory. Yeah. Questions? Yes.
Can the skills be hierarchically implemented? Or
in this theory, it's flat. Yeah, so it's flat. Unlike in metacognition, where there's a clear hierarchy, and it's probably always like that. This is a simplistic theory where there's like a flat hierarchy. A flat, no hierarchy, yeah. Yeah, so, I mean, you could try to do the theory with a hierarchy, but then you start introducing all kinds of other assumptions, and yeah, it's just not as clean. It seems very doable. So after this, we as I mentioned, we had this test, using frontier models. How well could they compose, and roughly the theory's prediction was correct. This So like Llama 7B at the time had even difficulty combining 2 skills, often would fail. And GPT-4 could combine 5 skills. Not with high probability, but reasonable probability. Okay. So then this is another paper we did. So that was for pre-training. The scaling laws and the study was for pre-training. So how quickly? So then the question we studied was: suppose you provide the model with skill-rich data. So the typical pre-training data may not be as skill-rich. So let's say you provide it with skill-rich data. So this is where that example, with the sushi and the ad hominem attack came from. So you start with some named language skills from Wikipedia. So they have they occur somewhere with a description in Wikipedia. Okay. Now, so every model in the world has trained on Wikipedia, so it will understand these. And we tested it. They all, they could all generate examples of these skills reliably, so they understood these skills, single skills. And then we try, they don't do very well at composing skills. So the training data we generated using GPT-4, and to combine K skills from categories, say, something like that, literary and rhetorical. Now the point is, these are only the first 2 categories, and the remaining categories are held out. We're not going to generate data on that. Okay, training data. So just from 2 categories, there are many sub-skills in those categories. We generate data. And then we evaluate, and so you fine-tune on it, on this data, SFT, and then you evaluate those fine-tuned models at generating the text combining K-prime skills from held-out categories. So these are not skills that you trained on. Okay? Questions? So the study is just saying, if you train on data that combines skills from these categories, how well can you do on these held-out categories? And we were actually very surprised. So K equals 1 data has effectively no effect, because of course they know the skills from Wikipedia and have seen examples. So, but for K equals 1 and 2, namely pairs of skills, it improves performance on K equals 2 and 3. And for up to triples of skills, it improves performance on 3, 4, and 5. So that's the graph here. And this is the last one. You can see that performance improved on 4 and 5 as well, just from training on triples of skills. So actually, this kind of improvement actually is not predicted by the theory that I mentioned. And this is very interesting, that somehow models learn to compose skills even better than that statistical theory was suggesting.
Excuse me, can we draw the standard errors on these numbers? Standard errors on these
oh yeah, these are on a lot of samples. I don't know, a few thousand samples. So I think these are reasonably accurate. Okay, yeah. So the model's learning of compositionality is stronger than predicted in the theory. So it generalizes to held-out skills as well. Yes.
One question. The model hasn't seen the composition of the skills, or
the composition, yeah.
But it has seen
Of the training skills.
But it has seen the
It has seen the skills.
Okay, that's
Yeah. Yeah. But it shows that if you consider behavior to be a ability to combine skills, it's showing that it's developing new behaviors that it had not seen in training.
To understand the way we evaluate on a composition on a pair of skills, is we create synthetic questions.
Yes.
On these 2.
And GPT-4 is the grader. Whether it, yeah.
So you have a powerful teacher to produce the questions and a powerful teacher to score them. Yeah. And the point
Because the questions are auto-generated. It's just list of skills and created. Yeah.
But they're generated by good.
Yes. No, it's generated by this Llama.
Oh, Llama.
Oh no, sorry. Oh, sorry. The SFT data. Sorry, the SFT data is by a good model, and the evaluation is on Llama. Yeah. That's right. It's just an SFT experiment.
Yes.
And actually, I would love to do this with RL, and I believe the data set is public. If anybody wants to do that RL experiment,
Do you know how
let
many,
me know.
how many questions you
It was a few thousand.
A few thousand.
Yeah,
And
it's in the paper. Yeah.
is it like with chain of thought, kind of like you have like some reasoning steps when you're training? Because I want to see like how.
No, not really. Yeah.
Really, and
Yeah.
it still like learns
Yeah.
to compose. That.
Yeah. So I'm actually, another thing I want to do is repeat this experiment with the think models.
It's 24, right? So there was,
Yes.
so it was impossible to.
Early 24, yeah.
Right, early 24, there was no reason.
Or maybe late 23, maybe it was late 23. I forget. Yeah. Okay. Any questions? Yeah.
In the previous results, trying to understand it, the skills that the theory assumed were disjoint in a way, right? Are the skills that...
The theory was agnostic about it, yeah.
So here, is it fair to say that those skills there are no shared component between them?
So that's the tough part, right? They're all language skills.
So is it that the stronger is because the skills are more overlapping on each other?
You're right that, they're all language skills at the end of the day, right? Yeah, you don't train on language skill and get better at soccer, right? So, yeah.
Thank you.
So, yeah, take it with that grain of salt, yes.
Do you have any insight about which skills are, like, sort of resist compositionality here? Like, let's say the metaphor skill, for instance? Would that
Yeah,
be
we didn't do that fine grain analysis,
Okay.
yeah. Yes.
Related to the last two questions, if like two skills are are skills that can be easily composed together, is there a relationship between those types of skills?
Yeah. So there's another point. Like some skills may be easier to compose than others, which also is hard to quantify with the limited data we have. Yeah.
One clarification here, like where are the solutions coming from that you're?
GPT-4.
So it's like a form of distillation.
Oh, sorry. Solution meaning grading.
Fine tuning.
Oh, the fine tuning one. Okay.
Yeah.
So that's also from GPT-4. Yeah.
So it's like a form of distillation that you're doing sometimes.
SFT. Yeah.
Yeah.
You want to call SFT a distillation.
And also for the theoretical result you were talking about earlier, where you have the 10x and the 2x, like where is that factor of 5 coming from?
From the chinchilla scaling law.
So that, like, if I had
From
a
the
different
theory.
scaling law with different power exponent, it would be a different factor there.
Yeah. So you shouldn't take that factor too seriously. For all we know, today's training with modern pipelines is different. Yeah. Yeah. Yes.
So, like, if the model can compose two skills, then naturally
No, it's not natural.
But you can just apply this twice.
There's a length restriction.
There's a length.
So right, number one. So there's a length restriction. So for k skills, you only get k minus 1 paragraphs, sentences. Number two, you're right. There's a cheating way to do it, right? Put k unrelated sentences, but the models are helpful. None of them did that. You say, create a sort of interesting paragraph, that's coherent, that uses all these skills. It doesn't try to cheat you and say, I'll just do the simple solution and make it unrelated.
My point is, if the model can compose two skills, then it can call this a new skill, and then compose this new skill with the third skill. You just need the ability to compose two skills in order to compose more skills.
But it doesn't seem to be like that from pre-training, right? Right? Because right, no, with fine-tuning, it can be enhanced. That's the whole point. That this is showing that whatever that circuit is that composes skills is easily learned from SFT. Yes. Sure.
So there are two ways to measure compositionality, right? One is where what you did by having the separate skills. But the other level, kind of compositionality, taking the same skill and repeating multiple times.
Yeah, we didn't do that.
Do you think there will be difference between that kind of composition?
I think so. So this task actually was very hard for us. We said, okay, when we created the data set, let's first take it ourselves, with k equals 4. And the rule was we'll give ourselves 2 minutes per question. And then that night, we are like slacking each other. This is hard. I can't do it in 2 minutes. None of us. We were taking 7, 8 minutes to do it. It's like very hard for the brain to keep these 4 things in your head.
Yes. The model gives a set of skills that compose together in some way to get the text. Or does it give a sequence of, okay, this is how you do it, and if you compose it in this way, in this sequence, then that...
There's no think tokens. This is, late 2023, yeah.
Okay.
So it would be lovely to see with your think models, the other open think models, what happens with this training.
We'll also do it in code, maybe.
Yeah. Okay. I'll move on to the next topic. Okay. Yeah, we're on time. Context enhanced learning. So with this, with the background I've given you, I find it very interesting to study this question of how skills emerge, and yeah, ultimately it's learning from textual instruction, right, or textual information, and somehow it's converting that into internal skills. So that whole process, what people were asking earlier, like where does that metacognition come from, etc. So I think it would be very interesting to understand that. So that was one of the motivations. There were other motivations which I'll mention for this paper on context enhanced learning. So let me tell you what it is. All right. So the background, of course, given today's talks, this is, you've seen it many times, this mystery of COT, right? Like if you ask the answer to be longer, include chain of thought, accuracy improves. And then the conjecture is that it's because it's allowing more compute. Okay, but then when you fine tune on this, as Alex was doing, you fine tune on that whole thing, right? So context enhanced learning is somewhat different. It's different from SFT. So normal SFT is, of course, say question answer, and you're computing gradients using next token prediction loss here. In context enhanced learning, there's all of that, both of those, but there's additional helpful information, okay, which is placed there by a teacher. So for example, the think tokens. All right, so the one analogy is that this is like a student solving homework, and the textbook is open before them. So think of this as a textbook. By the way, apologies for the change in fonts and stuff. This is my students' slides. The important thing here is that this textbook that's in context, you're not going to compute or do gradients on loss that's computed using that information. Okay, so you won't compute the loss, you won't compute any gradients. So it's there, and then you are going to do the usual kind of SFT here. Now that could be potentially still make a big difference, because having this, we know this about like K-shot and in-context learning and so on. Having this information here may improve learning over here, or reasoning over here. Now, this additional helpful information is presented only in training. So just like with the student having a textbook open when they're studying, the exam is not open textbook. So, all right. So that's the thing. So you are going to have it in the context, but not at test time. Okay. So can you learn so that you can still do well at test time? So by the way, I should mention here, like one of the things here was, I would sort of read these papers where like it's a kind of little mini industry, right? Detecting training data for LLMs. And it wasn't clear to me that gradient-based updates will always let you retrieve the training data. And so here, you're doing gradient updates here, but not here, but you're still training on it in some sense. And it's not clear to me that, and we'll see indeed, that you will be able to detect that this was available during training. So, all right. So these are some examples of helpful context, and this is known work. Okay. So for example, you could have few shot examples and then fine-tune using that, and URLs of the source of the data, because that has some information, thought-provoking guidance, etc. Okay. And this helpful context can depend on the input and the training step. So there could be curriculum. Okay. Any questions? Yes.
A small question: should the context be attached after the question or just before the question?
I forget if in the experiments it's in that order or not.
Because I have a feeling that if the model is doing something like reasoning, we first give the question and answer. Maybe the question.
I think we tried both ways.
Okay.
I'll tell you what the hurdle is in a second. Yeah. Any other questions?
So this is very similar to how people train instruction journey, right?
You mean like few shot or something?
Sure. Yeah. Few shot. Yeah.
So if you have few shot examples and then you don't do gradient. Yeah. So I'm saying these are existing examples. Yeah.
But the few shot, you give the few shot at inference time in the example.
Yes, that's the difference.
But now I think they're not giving it at inference. It's actually worse. It's like I train you to have access to few shot, and then at test time I don't give you the few shot. Right? Yeah.
That's exactly the issue. Yeah. So we'll see that.
It's a hard situation.
So you have to learn from the textbook, but yeah, I mean, just as we do, right? And then at exam time, you don't have the textbook.
But you have to know that at the test.
But okay, so just to give away the secret, right? You easily know how you did that, right? When you study for exams. Of course, you study with a textbook. And at some point you said, okay, I'll shut the textbook. Let me see if I can answer, right? Okay. So, and then it doesn't work, then you peek at it. And, okay, that's exactly what we do. Okay. Yeah.
In this setting, all that the LLM can do is it can memorize the textbook. It can't learn how to learn.
But it's not being allowed to do gradient updates on it.
No, that's why if it did the gradient computation,
yes, it could. Right, it would.
Then it could figure out what to prioritize, what to kind of learn from the textbook.
Yes.
But over here, all that it can do is memorize the textbook. Like whatever information is there, if it can pull that into its weights and keep it, right?
Yes.
And so when you come up with a new example without that, it can still pull that out because it's sitting in its weight somewhere.
Yes.
Right? So
that's the only way it can do.
That's the only thing it can do.
Yeah. But how does that happen? Yeah. So that's where Alex's point is very valid. Like, how exactly does that happen? Right. Yeah. Okay. So I'll tell you. So it has to be a synthetic task, right? So to avoid interference with its instruction, with pre-training and instruction tuning. So it's a multi-layer translation task. This is some input alphabet and there's an output alphabet, and it's a translation task, and there's like k steps in the translation. Okay, going from here to here is k steps. It's not a simple transformation from this language to this language, but it's simple in the sense that all the basic operations are basically two symbols going to two symbols, and then there's a circular shift once at every layer, like shift by one. The details are not important, but you get the idea. Okay. So the point is that each output symbol in the dth layer can depend on 2D input symbols. Okay. And because of the circular shift, like those symbols are distributed. So now the prompt, just to clarify the situation, I think most people are clear on it. But yeah, the prompt here is, if you just have input or output examples, you're trying to translate the sequence from this language onto language 3. Input is this, output is this, right? You get a lot of Q&A pairs, and then you would do SFT and hope to learn it, right? This seems very hard because there was this D steps in going from this language to this language. And just from input-output pairs, this seems very tough. even though it's a fairly simple circuit. You have to learn that circuit. And with context-enhanced learning, you're given the phrasebook or part of it or whatever, the relevant part of it, in the context, and then this example, how this was used to produce this. And so now you can sort of see, okay, this at least have the logic, right? This is the simple transformation, and see the pattern given this. The pattern is not explained, just this is given. But transformers are good enough to see the pattern, right? That BC went to something. Okay, so that's the setting. The details are not so important. And the theorem is that in a statistical query framework, and that is an asterisk but I won't go into that, learning to translate given these input-output pairs requires exponential in the examples. Okay? And if you do this in experiments, just input-output pairs, it's very difficult. Okay? It doesn't learn. But if you do it with context-enhanced learning, so now this phrasebook is going to be given in context. And so we're trying to do this. And we're going to use a suitable curriculum that I hinted at. So the first phase is to get it used to, and this has come up in all the talks on the think tokens, etc. Models have to be warmed up to the idea of seeing so much information and of this format in the context. So this is just like I forget what it was, Llama 8b. It's not used to seeing this gibberish in context. It hasn't made sense of it. So you first teach it to make sense of a phrasebook by using many random phrasebooks and productions. And then it learns this idea that to predict these tokens, I need to look back there somewhere in the phrasebook and do some pattern matching. So that it learns to do. Right? So that for a transformer seems easy, right? There are these random patterns appearing here, random patterns being applied here, and sort of does the matching and learns that I have to look there and look for these patterns. Then you train on a single phrasebook, which is a target that you're trying to make it learn. And now you do dropout. But you don't need to actually go to 100% dropout. You just do 20% dropout. And that already is enough to tell the model, wait a second, model meaning like the gradient updates, that, hey, don't rely on that information. Sometimes it's missing. So you better store it. And somehow that works. Okay? So with 20% dropout, you train it, and at test time, with 100% dropout, it still works. Now, dropout just means that those are blank tokens. So it still gets the compute. Question? Some question?
But isn't that like somehow you force it to learn the same thing?
Indeed. There's no way to translate without learning, right? But it's a different form of learning. It's internalized in some deep way, and it doesn't show up, it's in the paper, in terms of next token prediction. So the ways people have of detecting training data, those don't work. Yes?
Why not just do like a context distillation here? Like if you give it the extra information in the context, you have it produce the output. Yeah. Then you do supervised fine-tuning by taking away the extra information and trying to get it to implicitly learn that.
So we tried many things. This is all that worked really reliably. I'm not sure if what you have in mind is exactly what was tried also. So. Yes.
So here you use only one phrasebook for all examples.
Yes, that's the target that you're trying to learn. But you use random phrasebooks to get it used to the idea of I have to do pattern matching.
Can you?
Which is just a skill, right? It has nothing to do with that specific.
But I wonder, can you use them, different phrasebook during the training, and in the inference time, you may be able to use a new phrasebook, learn to translate some language.
That's true. Yeah. But you need it at test time, which we said will not be given. Yeah.
So the model also learns that skill. I see.
Yeah. So it does learn a new skill from text data, but somehow it's internalized in some. And actually, the paper does some mechanistic study of where it's internalized and so on. Yeah.
Yeah. Is it easier to learn the skill with a constant constant phrase book and then start changing? Or have you studied?
That didn't work.
Okay, because it may relate to my paradox about multiple annotations of the same questions. I'm trying to think if there's a connection here because, okay, when you're learning a skill, if you see the same question with multiple, maybe it's just easier to repeat. Don't change everything when you're learning the skill. So that's what I'm trying to do. But you haven't observed that.
Maybe we should discuss offline, yeah. What are interesting variants of this that we should try? Or you can try to, yeah. Yeah, this paper is on archive. So yeah, moving on. So yeah, that's just sample efficiency. You know, like our method just learns it and the other methods don't. Okay, all right. So dropout is required during training, but ICL capability is required. Yeah, and there's a mechanism. All right, so research questions for LLM metacognition. So I like to think in terms of theory and concepts. So what is a learning theory for metacognition? So we discussed speculation and what is this process and what is the mathematical framework or that describes it. This thing, you know, how does training on data exhibiting skill 1 improve skill 2? So just a general, you know, it's a concrete setting for OOD study, you know, which we are all interested in. How does the ability to compose skills emerge and what are limits on how fast this emergence can happen? I'm very interested with these recent think tokens, RL, you name it, and should be studied. And yeah, what are the scaling laws? So we saw some curves. Actually, there were 2 talks. One, there was a scaling law for SFT, and then in Alex's paper, there was a new law, and so on. Yeah, not clear. More questions. Leveraging LLM metacognition in training. I think metacognition can be used to give a much more high dimensional reward or signal or feedback to the trainer, to the model being trained. Right. So for example, this data set we had for compositional learning composition would be very interesting, and I think I will do this soon, just to RL on that same data set. As I was making this talk, I realized that's an easy one to try. Metacognition-based feedback in RL. This Llama 3 paper I mentioned uses skill annotated examples to improve math capabilities. Metacognition-based generalization of constitutional AI. So I think for safety and alignment, constitutional AI was this idea with 15 or 20 rules of behavior, which you can think of as very coarse skills, but you could flesh it out, and that's very possible. I've tried it, and you can get interesting skill catalogs for safety. And for auto-formalization of math reasoning. That's another project we have at Princeton. It's called Gödel Prover. It's the best lean prover, like the auto-formalization system for lean. It's like 10%. DeepSeek's model was 50%. This is 60%, something like that. So it's in the open, it's the best auto-formalization system. And the next thing I would imagine is that when you're proving theorems in lean, you have these tactics, which you can think of as skills of some granularity. So yeah, how to leverage that in training. To conclude, I think models are showing increasingly sophisticated metacognition. And it's clear that composition of basic skills, so they seem to all learn basic skills. Composition of basic skills trips them up, and bigger models are able to do it better. But so it's a big component of novel behavior, or regionalization, understanding, etc. Right? But it's not clear if that's all it is. It can learn skill composition through pre-training, and it can be sped up. We have suitable examples. And there's the compositional risk in AI safety. So if you think of behaviors as ability to combine skills in a certain way, we've seen that the model can learn to combine skills in ways it has never seen. So this is not discussed too much. Like people always focus on what behaviors were present in the training data, right, and make sure they are safe. But with reasoning and this kind of compositional ability, there could be other risks. Thank you very much. Yes.
So, is it a reasonable thing to do to think of these skills as some kind of latent variables?
Yeah, that's the way the theory is thinking about it. They're independent random variables.
Think of these as
latent variables, then do these does our understanding of what a skill is, does it need to necessarily map to what that latent variable is? And if there is no like mapping, how can we say something about cognition and metacognition? Because latent variable can be anything. Right?
So okay, so let's distinguish between theory, which has a sort of simplistic view just to be able to do theory, versus the full messy thing about skills, right, and metacognition. So those are two separate things. There's a very great fuzziness over here, and then in the theory it's all abstracted away. So let's not conflate those two. That's all. Did that answer your question? There's full messiness in the real world, yes. Yeah. But then how do you think about it? So theory always needs to make some simplistic assumptions.
Yeah. Okay. Yeah. So for your theory, how does your result aggregate if you move away from the prototype?
Yeah, then the theory, it just gets very messy to do. As I said, like if you have hierarchies and stuff, you get all these dependencies, and then probably there's no closed form theory, and you just do Bayesian calculations to get some.
So all the reasoning, for instance, is more mathematical reasoning related?
No, there are all kinds of, like the instruction following. Yeah. But we've done other things too, yeah.
Have you tried to use this reasoning for particular, I care about medical AI, something that you can see more in the context of solving a real problem in some real situation? How does that skill metacognition?
Yeah, I'd love to. But you would have to probably run it on your data, which is maybe private, but yeah. The procedures are very simple.
So, have you tried when doing the context-enhanced learning? Does the model becomes better at generating these skills?
So no. I think that's a very synthetic task. I'm not sure. It would be surprising. I didn't check whether it improves metacognition. I don't know.
All right, the speaker